Welcome to my final project video. My name is Sam Jacobson, and I'm going to be covering today the subject of LiDAR, how it is implemented in my project, and the overall goal of what we are trying to accomplish. So as you can see here, this is my target. It is a black bench located on the Mall of McKeldin. My motivation for choosing this target was its unique features as well as its color. The ability for an object to be black means it does not reflect light as well, so it makes it a little more difficult to scan. And the unique features of these slots within the bench make it a very interesting object. It's also very centrally located, and there are vast amounts of them across campus, which ties into the whole idea of this entire course. With remote sensing and LiDAR as a whole, we are attempting to recreate physical objects in a 3D space. The importance of this is wide-ranging. Personally, for me, I like to view it from a sustainability aspect, where we could create virtual maps in 3D space of our entire campus. And using this technology, we could save money and save resources when people want to visit campus, as well as demonstrate to the world just how beautiful it is without having to come physically see it. Overall, this course aims to build a 3D space of individual objects, but combine a series of them to create an entire map of the campus. That was also another motivation for my object, as these benches are located all over campus, on the mall, and around various buildings. So by creating one good 3D map of one bench, it could be replicated and moved around campus to be helpful with creating this entire 3D map. I've established why this work is important. I will now try to explain what LiDAR is, how it works, and how it is applicable to my project. So LiDAR stands for light detection and ranging. And light radiation is essentially sent from an emitter through some sort of medium, typically air for our case, off of the desired object and then back to the receiver. It is received at the receiver. A timer is stopped, which was started when the light was first emitted by the emitter. So essentially all LiDAR is taking that difference in time measurement and turning it into a distance measurement. And through very careful math and the overall LiDAR equation, we're able to get range data for different points in 3D space. Combining those with something like MATLAB, we can plot all those points together and actually come up with our own 3D object in 3D space. We can then put those things in something like MeshLab to try and form an actual physical mesh of an object so it looks perfectly normal like it would in real life. Types of remote sensing. There's active, which is something that LiDAR is, where it's emitting its own radiation and waiting for a signal back. Or there's something passive. One very good example of passive remote sensing is your eyes. Your eyes are not constantly emitting radiation. However, we receive radiation from the sun and off of other objects. And our eyes are actually the receiver, while the sun is the emitter. So that's a version of passive. Sorry, not active. That your eyes are passive remote sensing. The fundamental principles of LiDAR apply to our project, or my project, for mapping this bench. I have an emitter attached to my collection ring that I'll show you in a minute, that is shooting out light. It is traveling through a medium, air, and coming back to the camera that is reading that distance and that time measurement. And using that data and that collection process, I'm able to 3D map that in 3D space. So this is my collection rig. As you can see, down here we have the emitter, which is this line laser, and the receiver, which is the pie chart camera. I used a cell phone attached here with in order to measure the various angles at which the LiDAR could move and adjust to measure my target. I have an Arduino here, which powers the line laser, and the Raspberry Pi, which powers the pie chart camera, and ultimately can send data back to my laptop so that it can be processed. It is attached to a tripod, and it was two pieces that are super glued and duct taped together. In order to first start collecting data, we had to use a line calibration curve to calibrate the LiDAR, originally using a single laser, a single point laser. After doing that, I was able to find these ROC values with an H that does not change. These values I could input into my data collection process in Python so that my data could be properly calibrated to my specific LiDAR at several measurements and distances away from my target. Additionally, OpenCV, in combination with Python, is a package that allows the manipulation of images and video within Python. All an image is essentially a collection of pixels. So using OpenCV in Python was very advantageous because it allowed me to alter my data accordingly and filter it properly. Demonstrate my actual data collection process. We use a data collection Python code that using adjustable angles takes range measurements. I can then bring that into PyCharm and use something called color picker. And with color picker, I can pick out the red laser on my target, get that feedback of data, and then plot it. And then that actually using a data generation Python file will actually give me text for a series of 3D points that I can plot in MATLAB. So this is my field testing for the bench. As you can see, I have my field deployable LiDAR hooked up remotely to my laptop, where I can take photos using the Python script. Here I'm taking the front side of the bench, and I can adjust it using the various angles. Here's me taking it from another side of the bench. And in a moment you'll see how I can run the Python script of data collection, and then I can input the desired angle and it will take and capture a photo at that angle. So one problem with trying to do a black bench is there is very little refraction. So as a result, this was a big challenge I had to face. So I went out with paper and I actually wrapped it in white so that I could get better returns. And as well, if you can see behind, I put a black sheet over a box so that there'd be less noise when I did filtering. I also ran into issues with weather and time of day. So I had to make sure I went when it wasn't raining and when it was dark enough so that I could get solid returns. I thought the paper and box method was a really creative way that I was able to overcome these challenges and overall get better results. I could then import using the data generation script using my RO and RPC values for my specific LiDAR, and the glob function, which could get all of the photos from one folder and output them as a text file. I could then stitch together these text files in MATLAB, as I will demonstrate next. I could then import the various text files into MATLAB, and using these various functions, filter out any noise that I did not want so that I could generate a good looking point cloud of the bench. Before filtering, as you can see, there's a lot of noise surrounding the bench. However, afterward, we can see that there's clearly a more well-defined bench in the 3D point space. As you can see, my laser was pointed horizontal and the bench is slightly tilted, which is why this is not necessarily the best representation of the real-life bench in reality. Additionally, I only need to take 3 scans of the front, back, and one side because I could just mesh those all together and flip them in MATLAB so that I create a symmetrical bench. And then finally, here's that same point cloud translated into a PC cloud so that I could get the text file for submission. However, it did not show up great in the mesh lab, so here's an example of an old mesh lab I used. I could try and create a full 3D mesh. However, as you can see, mesh lab did not work great on my laptop, and with this mesh was not able to generate a perfect 3D mesh. That was my final project submission for ENME489Y. I learned a lot, and I feel like I showed my creativity through wrapping the bench and using a black background. I regret that my mesh did not come out perfectly and that my point cloud wasn't necessarily a perfect representation of the bench, but I think I did a very good job and I learned a lot about LiDAR and its fundamentals.